So chapter 13 kind of picks up where chapter 12 left off. And in chapter 12 we talked about HR diagrams. And HR diagrams are good ways of, we can use them as a scatter plot and throw stars up on an HR diagram. And the two things we're looking at with regard to the same star is what is the surface temperature of that star. In an HR diagram, that's along the x-axis, remember. The hottest stars are over here to the left, and they get cooler as you go over to the right. And remember, the surface temperature of the star then kind of is an indication of goes hand in hand with what color you generally see it as. And then along the y-axis is luminosity. How much energy is it putting out, is leaving its surface per second. And luminosity goes hand in hand with something we call absolute magnitude. And it increases as you go up the y-axis. So we talked in chapter 12 anyway about how stars, when they live their lives, the star's temperature and luminosity change. And chapter 13 then talks about the ends of stars' lives. And actually, there's this group down here we're going to start talking about, again, white dwarfs. So again, these are a couple figures from chapter 12. And your author had, I think, a good series of little photos there, images of what a low mass star undergoes as it lives its life. And so remember, as a low mass star, it kind of ends its life. This is a planetary nebula, and this is where kind of its outer material is kind of being blown off into outer space, or not really blown off like an explosion, but just kind of, I think, drifting off. And then what's left behind is a white dwarf. But if the star is more massive, generally than 8 solar masses, then it's going to live it's going to end its life differently. So these last two figures here on this, those last two little figures on this lower image here, this is the supernova explosion, and then this little dot right here, the little core, what's left over after a star goes supernova is either a neutron star or a black hole. In chapter 13, we're going to look more at that too. But what you're looking at here, I believe, is an image of a neutron star in the middle there. And neutron stars, although they're like stellar corpses, they do pulse, kind of like a heartbeat. It's kind of neat. So white dwarfs. Remember where white dwarfs are on the HR diagram. We saw them a minute ago. They're what I've called retired stars. Retired stars of low mass stars. Okay, they have no more nuclear fusion going on in their cores. Now, in this semester, we've talked about a star called Sirius. Sirius is in the constellation Canis Major, and sometimes Sirius is called the dog star. And we've also talked in this class that oftentimes stars like Sirius can have a companion. They are gravitationally associated with each other, and they orbit what we call a common center of mass. And Sirius, actually, when we look up the nighttime sky, it's a really bright star, and it actually has a companion called Sirius B. And you can see down here that Sirius B actually is a white dwarf. So Sirius B must be what? A little more massive than Sirius A. So it's a little bit farther along in its evolution than its Sirius A. Sirius A is still fusing hydrogen in its core, so it's still a main sequence star. So this is what the pair, and you can hardly see, this is Sirius B down here. Look how dim that looks, because it's retired, right? This is what the pair stars look like in the visible region of the electromagnetic spectrum. But now look what happens, because Sirius B is a little bit brighter than Sirius A if you switch wavelengths that you're looking at. This is looking at ultraviolet and X-rays. So that, I just think that's interesting, where this is these pairs of stars. So Sirius B is the retired white dwarf, and Sirius A now is a little bit smaller in X-rays and ultraviolet. It's actually a main sequence star. So just to kind of remind you, this is an HR diagram showing you kind of what our sun will do, right? It will leave the main sequence and it will go up here and become a giant, and ultimately it will create a planetary nebula, and the core will cool down, and that's what we call a white dwarf. So that's kind of what we talked about in the previous chapter. So as the now retired star, as it lived its life, it went through a few. Its core took a beating, is what I say, and that is that gravity kind of compacted the material down and down and down and down. And so if you were to visit a white dwarf and you were to be able to take a small amount of that white dwarf, it would weigh a lot. So it's very compact material. In fact, a white dwarf that is about the size of our sun would be compacted down. It's about as massive as our sun would be compacted down to the volume of our Earth. One thing I think is kind of interesting is that the higher mass white dwarfs, like you see, instead of 1 solar mass, this is a white dwarf that's 1.3 solar masses. Notice that it's a little bit smaller, even though it's more massive. And it's its mass itself that squishes it down. What we're going to see here in a minute is there's a limit that a white dwarf can be. If it's more massive than 1.4 solar masses, what we say electron degeneracy can't hold it up anymore. Okay, so a white dwarf is still kind of normal matter in that we think of normal matter as having a nucleus. Within the nucleus we have protons and neutrons, and then we have electrons outside the nucleus. Well, generally matter cannot coexist with other matter in the same space because of what we call electron degeneracy. The electrons around the electrons won't squish down anymore. And that's kind of what we have supporting the weight of a white dwarf, a retired star. So I mentioned the 1.4 solar masses. There is this limit that you cannot have. Something else has to give, so to speak, if the mass of your white dwarf is any more massive than 1.4 solar masses. But kind of getting away from that a little bit, I want you to think about a pair of stars, could be Sirius A and Sirius B, and the pair of stars is such that over here on the right, that's our retired star, white dwarf, and over here on the left, that's our main sequence star. And one of the things we know about main sequence stars is that as they leave the main sequence, they swell. And so what really happens out there in binary, close binary star systems like this is that the swollen giant actually can dump material, just like you see in this picture here. It can dump material from itself onto its companion, its retired white dwarf. Now you got to picture this little stream of material that's coming from the giant and dumping onto its companion white dwarf. That's really hydrogen. I mean, it's basically kind of outer material that wasn't near the core, and so it's fresh hydrogen. Well, in this chapter we talk in a couple places about something called an accretion disk. And what an accretion disk is kind of, I've heard it described like water kind of getting, most of the water is out of your bathtub. You know, you pulled the plug and the water's gone down, most of it's gone down. And as the last bit of it goes down, you can start to kind of see this swirling disk of material that's kind of in queue to go down your bathtub drain. And that's kind of what we have when we think of an accretion disk. You know, gravity is pulling that material, the fresh hydrogen from the giant star, into kind of a queue, a disk, to getting closer and closer to that retired star, that white dwarf. And kind of when you take your hands and rub them back and forth, that's kind of what we have going on in this accretion disk. That is fresh hydrogen around our white dwarf. So what can actually happen, and does happen, is that the material in the accretion disk can heat up more and more and more, and eventually, now you're going to have to kind of bear with me because I switched directions here. Now the white dwarf is actually on our left, and the main, or I guess not the main sequence anyway, it's the giant companion is on the right. But what can happen is that the material in the accretion disk can get hot enough. Now this is material coming from that giant star in queue to land on that white dwarf. It can get hot enough to begin this kind of unbridled explosion. We can have nuclear fusion. I know it sounds kind of strange, but those hydrogens can get moving fast enough that they can slam into other hydrogens and fuse to form helium. And that's a very explosive, relatively explosive event, I should say, not as energetic as a supernova, but we call that event a nova. So basically what a nova is you have this situation I just described, a white dwarf and a companion kind of giant star, and the white dwarf is getting material that's falling into an accretion disk. That material is heating up and it goes, and that's called a nova event. Now, one of the cool things about nova events is that, can you see where after it kind of blows off, that's just the accretion disk, and what's neat is that the white dwarf itself remains intact. So as long as that companion star wants to dump some more on the white dwarf, it can do it again. So this is not a very good photo, but of a nova event occurring. So what will happen is where that the disk area around that white dwarf will get really bright for a little bit, and then it will dim back down to normal. And like I said, nova events can reoccur in the same binary system.